Yeah, good morning, everyone. So as Sam mentioned, this is the second part of kind of the plan for the Atom Probe talks. Now, originally I had kind of planned on doing both Atom Probe data reconstruction and analysis in this webinar. In practice, I found that just covering the reconstruction was maybe enough for one webinar, so possibly going over analysis of Atom Probe data at a future date. So it's just going to be the reconstruction that we'll focus on today. So what I would like to talk about is to start by just reviewing essentially an atom probe experiment showing where data reconstruction lies within the whole flow of the experiment from start to finish. And then kind of get into the details. Talk about atom probe reconstruction in terms of spectral calibration and ranging, spatial reconstruction, and a bit of discussion as well on some artifacts that can happen during atom probe reconstruction, as well as some of the limitations we have. Then I'd like to kind of summarize everything by going through a fairly straightforward example of a reconstruction using a steel sample with a heterophase interface. And I'll do this using the commercial IBAS software. So starting again with our kind of atom probe overview. So to refresh, an atom probe experiment has kind of multiple steps to it. First, of course, we have our starting material, and we need to form that into an atom probe specimen. These are these nanoscale needle samples that have that shape because basically we need to get down to that fine point so we can concentrate the electric field at the tip such that we'll get field evaporation to occur. This is the process that happens during the next part of the atom probe experiment, the data acquisition. This is where a material is essentially picked apart atom by atom through successive field evaporation using either a pulsed voltage or pulsed laser in the presence of a high electric field. This is the part of the atom probe experiment that actually uses, the atom probe tool itself. And so far on this kind of process flow of an atom probe experiment, from starting material to data acquisition, this is what we covered in the last webinar. So if you want to refresh on that, you can look that up. But then the next part of the atom probe experiment, the data reconstruction, will be what we covered today. And that's really when you're taking the output from the acquisition stage, which is not, immediately kind of readable to get your scientific observations, and using that to build your, 3D model of your material that you can then analyze to make your observations. So the goal for atom probe reconstruction is to essentially end up with, a fully complete atom probe data set, which is basically a 3D model where we have the spatial positions of all the atoms, in our reconstruction, and a mass spectrum, or a mass to charge ratio spectrum to be precise, where we have all of our different peaks identified as belonging to, an element or combination of elements. And then this is the point when, you can start your analysis to look into the microstructure of your sample, and make your observations. But really always keep in mind, you're making these observations on the model you make with the reconstruction. So really every step of the whole process is important, the reconstruction quite critical. So let's go into the details of a reconstruction, how you make it, and what are some of the factors that lead into it and can separate a good reconstruction from a bad one. So as I mentioned, data reconstruction is really the process by which we take the output data from the atom probe and convert it into the 3D model that as best as we can represents the original material. Now, sometimes atom probe reconstruction can be fairly straightforward, and using the commercial software can be done quite easily. But I don't want anyone to kind of underestimate this. Reconstruction can also be a very difficult and quite involved process, often requiring kind of different approaches based on your sample, how it evaporated, as well as what other types of information you might have available. Also, something to always keep in mind is that, before we evaporate the sample in the atom probe, there is kind of one true configuration of the original material. At one point, all the atoms are locked in place, and that's what we want to get to. But we might not always be able to do that, right away perfect, especially not first try. Sometimes reconstruction can be an iterative process where, you build a reconstruction, you do a bit of analysis, you maybe see areas where the reconstruction isn't perfect, something that needs to be changed, you go back, try and improve it, maybe bring in more data to help. Also, sometimes you can just never really get to that perfect model of your material, both because of limitations in the resolution of the atom probe, but also just some limitations in the field of operation and reconstruction process. Something to keep in mind is that an atom probe reconstruction, you can sometimes get to the point where you have a globally accurate reconstruction that is maybe, a representation of the overall shape and, distribution of phases in your sample, but it might have local inaccuracies, especially around, small phases, defects such as interfaces and so on. Now, in all cases, reconstructions will primarily involve two main steps. First being the spectral calibration and ranging, where we're looking at essentially the mass spec side of the atom probe, and then that spatial reconstruction aspect. So let's go through those now. First of all, looking at spectral calibration and ranging, keep in mind that part of the information we get from the atom probe experiment is essentially time of flight data. And that's the time of flight between the incident pulse of either the voltage or laser onto the specimen and the detection, of the ionized atom leaving the sample. And what we need to do is first apply some corrections to the time of flight data, which we can do to try and improve the overall signal, affected by both the voltage that the sample was at when the ion departed, as well as correcting for the position effects due to the position of the tip, from where the ion departed, and that's known as the bowl kind of correction. And just to show a little map there, I'm showing what a bowl correction looks like. Is basically the different flight paths will come from being at different parts of the tip and the projection of that course through the electrostatic field. So slight corrections in time of flight to improve that spectra. Then what we need to do is basically convert that to a mass to charge ratio spectrum. And we do that by aligning essentially to known values. This is usually done in the first case using a parametric fit in the kind of instrument calibration on a known material, like say a sample of pure silicon. But then what will usually be done by the user on top of that will be a kind of a linear fit, and that will be based on user input for that exact sample and data set that is being reconstructed. And again, this is done using known peaks within the material. Then what we need to do is kind of look at the remainder of the mass spectrum. So now we're looking at the mass to charge ratio spectrum rather than the time of flight spectrum, and assign the different peaks ionic identities. So this is known as ranging or ranged ion assignment. And it's called that because basically we are going to assign a range of mass to charge values, so essentially on this x-axis on the images in the bottom here, as defined by a peak in the spectrum. So what we have to do essentially go through all these peaks and say, each peak corresponds to an element or a combination of elements. And what we do to help us identify that is take advantage of the fact that in atom probe, since it is a mass to charge ratio spectrum and we can see the different masses of the different elements, this gives us the ability to resolve different isotopes. And for all terrestrial elements, at least those having not undergone radioactive decay, we can expect that the isotope ratios should meet well-known natural abundances. And so basically what this allows us to do is look at our mass spectrum and compare the peaks we get to what we would expect for the different isotopes of a given element at a given charge state. And so to kind of show this as an example, let's say we have our mass spectrum as we have shown here below, and we're interested in identifying the peak at mass charge ratio 28, so 28 Dalton. And if this is, say, a steel that has a fair amount of silicon in it, we know that both iron and silicon would be present in this sample. And if we look at it, then we say that the peak at the mass charge ratio of 28, it could belong to silicon, the major isotope of silicon in the 1+ charge state, which would be exactly at 28. But it could also belong to the major isotope of iron, iron 56, if it's in the 2+ charge state. Because since it's the mass to charge ratio spectrum, the mass divided by the charge state, being a 2+, would take that 56 down to a position at 28. So how do we know which element that peak would correspond to? Well, what we can do is also compare it to the other isotopes. So if we look at the silicon, we see that we also have isotopes appearing at 20.
Brian,
Yep.
sorry to interrupt. There's just been a request if you could slow down a little.
Oh, okay.
Thanks.
All right, I'll slow down a little. So let's say then we're looking at the silicon. So if we take, if we look at the different isotopes that we have there, we see here we have one at 28, we have one at 29, one at 30. And the heights of those blue lines would represent the natural abundance, the ratios rather, or the amounts we would expect if we satisfied the natural abundance ratio. So, in other words, if we were to have silicon as represented by that peak at 28 Dalton, and what that would mean is that if we were hitting the natural abundance ratio, we would expect peaks at 29 and 30 as high as those blue lines on that graph. And what we can see from our actual mass spectrum is that we basically don't get to that point. In other words, there's not enough silicon, or there's not enough of those peaks for that 28 peak to be entirely made of silicon. Now, if we compare that to what we see with iron on the right, we see the other isotopes of iron that would appear at 27, 28.5, and 29 Dalton all have peaks that match the expected values based on the natural abundance ratios. So we can be a lot more confident then in assigning those peaks to iron. Now, this is the kind of a process we would repeat and continue throughout the entire mass spectrum until we've identified, all the different peaks there. So then this brings us to the spatial reconstruction stage. And one of the main aspects of this is in defining how the radius of your sample, the radius profile, so radius with respect to Z, can be defined. There's a few different ways we can do that. So one of the most common is to use the voltage profile. So this is the profile of the voltage of the specimen versus detected ion. And this is because we expect or can assume often that when we have an atom probe experiment evaporation occurring, we'll be at relatively constant evaporation field, which according to that equation shown on the left would mean that the voltage and the radius will be proportional to each other. And so as we see the voltage, which is adjusted to maintain evaporation, as we see that voltage vary, we can assume that is proportional to the changing radius of the sample, which of course starts very small at the very tip of the specimen and gets larger as we evaporate successively more material. Now, this is a fairly good assumption if you have a homogeneous sample, for example, a single phase or a dilute solid solution that is, running well, kind of well behaved, doesn't run through many defects, and also a case where you're not doing a lot of changes in running conditions. So, for example, not, imparting a large laser energy or changing too much, those parameters. In which case, because then you can still assume that you'll be at a constant field and that proportionality between the voltage and the radius will remain constant. Now, another way that you can define the radius profile is more kind of geometrically, and this is by using a shank angle and an initial radius as inputs, and then kind of essentially building a reconstruction based purely on the geometry of those given by those factors. Now, this is good when you have a more inhomogeneous material, or so in other words, you're not going to be satisfying that kind of constant relation between the voltage and radius, or if you happen to be varying running parameters. A kind of extension of that is to also do kind of a tip profile reconstruction where you are kind of basically a variable shank angle. And now normally we would be measuring the shank angle from an input, TEM or SEM image. In the tip profile, you're kind of using the exact profile based on that image. Now, this is good for inhomogeneous materials, particularly when they don't mill uniformly in the fib. You know, you might have different phases that lead to an overall sample shape that's not of a uniform shank angle. So you can more easily or more kind of perfectly match it by building a tip profile. Now, to show an example of how this different radius evolutions can affect your reconstruction, we can take an example. This one's from Kamika, where they've taken a known standard of nickel chromium in alternating layers. And you see on the bottom left the voltage profile of such an experiment. You can see that it varies quite a bit going up and down. It's not kind of constant or uniform. And this is because the different layers, the chromium and the nickel, have different evaporation fields. So we can see if we were to try and build a reconstruction using the voltage to define our radius evolution, we end up with something that we show here in the middle, where we can see that kind of pagoda-shaped structure. So, you know, it's non-physical, as well as we're not matching the thicknesses that we would expect for this known standard. And this, again, is just because of the different evaporation fields of those materials, therefore violating one of the assumptions that we make if we were doing a voltage profile, in that we can expect a constant proportionality between the voltage and the radius. Here, the different materials mean we can't. So in this case, what was done is switched to a tip profile reconstruction, where they've taken one of the images of the sample, and it looks like it was done following fib milling, defined a radius evolution based on that. And you can see that the reconstruction that results from it, showing on the top right, is a lot more representative of the original material. Not only did we lose that kind of weird, zigzag structure at the edges, but we also are able to get the layer thicknesses very close to what was expected from this standard. So of course, there's a lot more involved in the reconstruction. That's kind of just one of the initial factors that we have to account for. Overall, when we're performing the spatial reconstruction, we're trying to get those 3D coordinates for each ion that best represents the positions in the sample. And we get this from the XY detector positions, as well as the sequence of evaporation is what we then use for the Z increment. So when we're determining where in XY an ion should be positioned, we have to factor in the magnification of the tip at the moment of that ion's evaporation. So this includes such factors as the sample geometry, in other words, such as given by the radius evolution model that we've chosen. And depending on that model, that will also include different inputs. So if we were choosing a voltage profile, we would have to use the input as the voltage at the moment of the evaporation, as well as value for the proportionality constant. If we were using other methods, such as, say, the shank angle, then we would need those inputs as well. And then also the XY factor will be affected by something known as the image compression factor. And this is essentially just due to the deviation of the actual flight path of the ions from a perfect hemispherical projection. And this image compression factor essentially has its origins in the fact that our sample isn't, a perfect sphere floating in space. It does have kind of a shank of a needle specimen going in behind it, which can affect the shape of the electric field. So the ICF, or image compression factor, will vary, kind of from sample to sample. And so then in addition to knowing the XY position, we also have to then increment our Z position for each successive ion that was evaporated and then is reconstructed. So to do this, we need to make some assumptions then about the atomic volume. In other words, the actual physical space that atom occupied, that gives us essentially the difference in Z between it and the ions that were behind it. Also, then we have to increment it. We have to know essentially our sample geometry, because that's going to be affected by the radius as well. And we have to know our detection efficiency, because just a reminder, in AtomPro, we evaporate every single atom, but we don't necessarily detect every single atom. And so depending on the detection efficiency of our atom probe, we have to account for those missing atoms when we build our reconstruction. Otherwise, it will be, essentially a falsely compressed, data set. So to show this kind of schematically, we have this figure on the right, and it's a little maybe confusing at first glance. So I'll kind of talk through it for a second. So here we're showing a crystalline material that clearly has atoms aligned on kind of crystal planes separated with a given d spacing up there. And if we assume then that we have evaporation in the order given by the sequence of those numbers, where we're of course always kind of having the surface atoms evaporate and then successive atoms behind it being evaporated as a new surface is revealed, what we would then see if we were considering, just the reconstruction in X, I guess, because we're only considering this in a 2D case, is kind of shown in that middle figure there. So basically, we see the detected order from top to bottom as we would input it, say from our detector, and we can identify the, let's say, X coordinate of those different atoms, get them into the right position. But then to fully fill the reconstruction, we have to increment that Z coordinate. And so you can see that if we are even putting in a constant, kind of Z spacing there, but we're doing it appropriately with respect to the sample radius, we will be able to get a good approximation to, the original plane spacing positions of those atoms. And so that is kind of just a good representation of how these reconstructions can get built. Now, I'd like to just show a figure here that shows kind of basically how the reconstructions can vary if we start playing around with some of the different input factors. So what we see kind of on the center is basically a well-made reconstruction with the input parameters that would build a good reconstruction. But then for the sake of demonstration, 3 of these factors, the detection efficiency, the field factor, and the image compression factor, are changed. And we can see the effect of that on the reconstruction. Now, you might look at this figure and then think, well, how can I trust any atom probe data now? Like, you look at how much the user can put their fingerprints onto it, and they can change it for reconstructions that look nothing alike anymore. So how can we actually be sure that any atom probe reconstruction is valid for analysis? And to that I'll say, to a certain degree, that's true. You should always kind of consider an atom probe data set as guilty until proven innocent. But at the same time, there's a lot that we can do to actually, make sure that we can trust our atom probe data. So first of all, I'll say as a kind of a general caveat that in this case, we're clearly taking these factors to extremes, to show their effects upon the material. So, it's not as, material might not just be, it's not always going to be as sensitive as that. But there's basically a lot of things we can do to help build our reconstruction so that we know that we're not, completely out in terms of its veracity. So for example, let's say with this material, we knew that the precipitates within it, say we've done prior TEM, were, spherical or spheroids. Well, right away, we can see from just visual inspection then that, the really high or really low field factors won't give us a representative material, because we're either going to end up with precipitates that look like needles or precipitates that look like kind of pancake shaped. So, right away that kind of takes us, taking in a bit of prior information can help us right away kind of narrow in on a reconstruction that looks a little bit more valid. Also, we will know a little bit more about our material, and our atom probe. We know, so for example, like with detection efficiency, between something like 0.3 and 0.9, we should be able to get a good estimation that will take us a lot closer than that, which is a very wide range. Finally, there's other ways in which we can kind of calibrate the data set that I'll talk about in a moment. But then finally, as kind of just a way of saying, how much we can trust the atom probe data, one thing I want everyone to note when looking at this figure is no matter how much this data set is stretched and squished and taken kind of the funhouse mirror to it, one thing that never occurs with it is the atoms are never shuffled. You never have an atom that's completely rearranged with respect to the other atoms. And because of that, you can say that basically, well, if you wanted to know, for example, the composition of the precipitates in this material, You could get that from any one of these reconstructions, because the composition, which is just essentially a binning of of a phase and counting the atoms within it, isn't going to be changed by different distortions of it spatially. So, and you can kind of extend that concept forward, which is to say, if I just want to know composition, maybe I don't need an absolute, atomic scale perfect spatial, reconstruction, because I know that, even if I'm a little bit off, the composition will remain the same. But also, say, okay, if you were interested in different spatial factors, then maybe you would have to say, well, I'll need a better reconstruction then. Like if you wanted the radius of these precipitates, then you would have to get a reconstruction you can trust spatially a lot more. So part of the whole process in reconstructing atom probe data and then doing the subsequent analysis is knowing how far you can take the analysis, given kind of how well you've been able to do a reconstruction and how much you can trust the final material model that you build. And so as part of building that kind of, trust in terms of spatial calibration, there are other pieces of information we can bring in. So, I already talked about the idea of bringing in a, TEM or SCM image to help, build profiles on the specimen. You can also take some information, from the atom probe, from other aspects of the atom probe data. In this case, if you have a sample that is, metallic or other well-behaved crystalline sample, you can often observe crystal poles in the detector event histogram, seen as that kind of hemispherical projection of the tip. And this is due to very slight deviations in the evaporation field based on, the positions of the atoms within the crystal. And what we can do is essentially use that to give us an idea of how the tip is projected, which can help us define an image compression factor. What we can also do is look at the reconstruction directly at those poles, where we could expect the resolution kind of for those given planes corresponding to that pole to be highest. And we can map the d-spacing at those poles and basically compare it to known values for that material. So in this case, with aluminum and the 111 pole, we can look at the d-spacing that we get at 111 and compare it to the known d-spacing for aluminum, then adjust our reconstruction parameters accordingly until we get a d-spacing that works. And we can do that for the other poles as well to kind of help build our reconstruction spatially calibrated. So there is other information that you can bring in. But sometimes that won't always be the case. So I'd like to talk a little bit now about atom probe artifacts and limitations and how this can affect the final reconstruction that we create. So first of all, a word about assumptions. Different reconstruction protocols, they all make different assumptions, and some are common to nearly all reconstructions, and samples of which being, we almost always will assume we have a hemispherical tip shape during evaporation, that evaporation is uniform across the field of view, that the radius evolution during evaporation can either be mapped by the voltage curve or the initial sample shape. In other words, we can use that voltage profile mode or a mode defined by initial imaging of the sample. Also that we, when we're determining our reconstruction parameters, a lot of times we assume that they'll remain constant throughout the data set. For example, the image compression factor or the detection efficiency, and sometimes that might actually change a little bit and might input limitations in the data. Finally, we also assume that the position of an atom on the surface of a material when it evaporated was its original position within the material. In other words, as we're evaporating material and we're exposing new surface, wherever the atom departed from is the position that we're trying to reconstruct to. So we assume that that initial departure position represents the initial position within the material. In actuality, what can happen is, especially for very mobile elements, that when they're exposed to the sample surface and by evaporation of the atoms on top of them, they might move a position or two, roll up onto different positions, especially high field areas. And therefore we might end up with slight deviations between where we put the atom in the reconstruction and where it originally was prior to evaporation. So the thing to keep in mind in knowing these assumptions is because when these assumptions are violated, artifacts and aberrations can appear in the reconstructed data, or we can have spectral or spatial resolution degraded. So we saw that, for example, thinking back to that nickel-chromium alternating layers, if we assume, or we violated in that case the assumption that for a voltage profile, the ratio between the voltage and the radius would be constantly proportional, and we ended up with this non-physical reconstruction. So we have to keep this in mind when we're building our reconstruction so that we know how far to take the analysis. Another common artifact that we can get in atom probe when we're doing, especially the spectral reconstruction, is with overlapping ions in the mass-to-charge ratio spectrum. And this is usually caused by essentially having, integer multiples of mass and charge. And this can then make it indistinguishable as far as the atom probe is concerned by using the time of flight, since both of those factors will affect its position and its time of flight. So we saw, for example, when we were speaking before about the ranging that peak at 28 Dalton and whether it could be silicon or whether it could be iron. And that was a pretty straightforward case because, iron was the, solvent element in that sample. And, it was very clear that the silicon, we didn't hit those other isotopes. But sometimes it can be more complicated than that, especially in cases when we're looking at lower abundance elements in the material, where we won't necessarily have sufficient counts of the more rare isotopes to be able to fully determine whether a peak belongs to one element or another. We can also run into that problem if we're looking at elements that have no other isotopes, because then we kind of lose that ability to guide us in the reconstruction. Taking, for example, if we were looking at aluminum, in aluminum, the 1+ charge state will appear at Dalton at 27, which overlaps with an isotope of iron in the 2+ charge state. Aluminum, essentially monoisotopic, it will not really, we can't really use any other isotopes to see whether or not there would be, we can expect that peak to be aluminum or not. We'd have to only be looking at the iron peaks. So we might say, well, maybe a small fraction of that large peak is aluminum, and we can't really tell. So the best way we have of kind of working through this problem is by deconvoluting the mass spectrum to try and quantify how much overlap we have. And that, again, is a situation where we're leaning on the natural abundance ratios. And so we basically can say, if we look at the different heights of the peaks, how much do those vary from the natural abundance ratios? And can that variation be explained by the presence of another element? So this example, again, of iron and aluminum, if we were to look at the peaks of iron and then we saw that, well, maybe, we expect aluminum in the sample and maybe that peak at 27 Dalton is 5% higher than it should be, even though the majority of that peak is still iron, we can maybe say, well, then 5% of that is probably aluminum. And we can then use that in determining the composition and essentially quantify that overlap. The difficulty there, though, is that we still have no way of saying which of those atoms was aluminum and which ones are iron. We can only say, 5% of them in this bulk are likely aluminum, but we don't know if, they were the ones over here or there at the interface or in the bulk or so on. Another common error that we can get in atom probe data is something known as local magnification or trajectory aberrations. And these we get when we have variation in the evaporation behavior due to different materials that might evaporate more easily or with more difficulty than the surrounding material. So looking at the figure at the bottom there, so let's say we, for example, have a precipitating material that might be either low field or high field. In other words, it can evaporate at a lower field or more easily, or evaporates at a higher field or with more difficulty than the surrounding matrix. And what can happen in that case is we end up with a deviation from the ideal hemispherical tip shape. Remember that assumption. either in the case of a low field where it kind of begins to flatten out and goes, concave, or the high field precipitate where it kind of bulges out as kind of convex. And this can also be caused by other structural defects. Now, because in Atom Probe, our tip is essentially our optics and how it shapes the electric field, this local alteration of the electric field around that feature can affect the overall trajectory and therefore either compress or magnify, so magnify or demagnify that feature. Also, depending on the exact ion trajectory deviations, we might even end up with essentially overlap, or ions that appear, say having matrix ions appear within the region that should be the precipitate, or vice versa, and that can actually affect our composition measurements. This also goes back to what I mentioned earlier about the idea that we could build a globally accurate reconstruction and still have local inaccuracies. So let's say we had an aluminum alloy, with precipitates in it. We might use our, spatial plane spacings to properly calibrate that aluminum, by looking at the matrix and say, yes, we've got all the aluminum peaks, the d-spacings are right. Overall, we have the exact shape of our sample. But when you look at the individual precipitates, if their field varies significantly from the matrix, we could end up with them, magnified or demagnified. We could end up with ion overlap. And this basically means we have essentially local inaccuracies in a globally accurate reconstruction. So always something to keep in mind. Now, these are just a couple of the kind of main limitations and artifacts we can see in Atom Probe. I'd like to go over a lot more in more detail, probably when we go to talk about Atom Probe data analysis. For now, I'd like to then just kind of summarize everything that we've seen, in the reconstruction by going over an example of an Atom Probe reconstruction using the commercial software of IMS. And again, I can't say that CCM, condones or supports or is any way, benefiting or linked with Kamiko, which is the company that makes this software. It just happens to be the brand of our Atom Probe, our Elite 4000 XHR, and then the software that we'll use accordingly with that. It's also the most common, Atom Probe reconstruction software there is here. So for this sample, this is a sample that's a mixture of ferrite, which is BCC iron with some solution elements, and nanoscale perlite. And perlite is a mixture of ferrite and iron carbide, Fe3C, or cementite. And what we want to do in this sample is look at the interface between the ferrite and the nanoscale perlite, especially at those carbides. Since we were, of course, seeking this very fine feature of interest, we made our sample using the FIB. We created our lift out such that we had our ferrite at the top and our nanoscale perlite at the bottom. We ran our acquisition, collected a good amount of data, and now we're ready to do our reconstruction. Just to comment on essentially data acquisition and file transfer. So using again the kind of Kamiko system with our 4000 XHR and IVAS, following data acquisition, the Atom Probe will write the data, the acquired data, into a .rhit file. This proprietary file format contains information on the instrument, the acquisition, as well as all the data obtained by that from the Atom Probe. And then that .rhit file is what you can read with IVAS to be able to form your data reconstruction. What we're looking to make when we finish our reconstruction is essentially two files. One is this .pos, or position file, which for every reconstructed atom, or ion rather, contains the XYZ spatial positions, as well as the corresponding mass to charge ratio. So this will be unique to each reconstruction. But then also we'll look to contain this .rng, or range file. And this is a simple file that is basically contains our ranging info. So it tells us what peaks we want to identify to different ions or elements or combination of elements based on these ranges of mass to charge. So when you're reading a POS file, with the software, it needs a corresponding range file in order to interpret, what to make of the different peaks within it. And a range file could be used, with multiple reconstructions as well, because if you know the peaks, and they're going to be common between them. Like I said, the pause file will be unique to a given reconstruction. But you could also still have multiple reconstructions or multiple pause files made, for a given data set. So when we go to start our reconstruction, the first thing we're looking at is essentially a summary screen that just says a lot of the information about what came off the atom probe, how the experiment went, as well as comments, put in by the operator. So then the first thing that we want to do when we start to build a reconstruction is we need to select the ion sequence that we're going to reconstruct. So this is by looking at the voltage curve, which again is a plot of the ion sequence, so essentially from the first to the last evaporated ion, or detected ion rather, and then its corresponding evaporation voltage, which of course is varied throughout the experiment. And so at this point, we use that kind of selection box that you see there to pick the part of the data that we want to reconstruct. Now, in this particular case, we're going to reconstruct essentially all of the acquired data. So that box is selecting essentially from the beginning right to the end of that curve. Then what we're looking at is we look at the detector event histogram. So this is essentially a map of hits on the detector. And here, what we want to do is choose the XY detector coordinates that we will be reconstructing. So essentially, if we have that kind of inner circle that you can see drawn there, and that is drawn within, the area where we're receiving hits on the detector, and that defines, atoms within that area of the detector are what we'll use to build our reconstruction. The next step takes us to looking at the time of flight spectra. So in this case, what we want to do is start by running some iterative corrections to try and improve the overall peak shape and mass resolving power by basically correcting for differences due to the departing the voltage at which the ion departed, as well as the bowl correction, so the corrections for the position on that tip. This is done kind of iteratively with measuring the full width half max of a given peak to try and improve, like I said, the mass resolution. The peak that you choose to run your sample should essentially be a major peak in your system, something that is present at all stages of the evaporation, so that it's present at all different voltages, as well as present uniformly across the tip, so you can work that bowl correction on it as well. In this case, we didn't really see much when we did the change, and we did get a improvement in the full width half max from about 900 to about 1,000. But it just goes to show we already had, a pretty good data. We weren't able to really improve the mass resolving power that much more in this case. Finally, then what we need to do is do the mass calibration. So in this point, like I said, we're applying essentially a linear fit using known peaks to improve the positions of our peaks. So good practice for this is to usually choose 3 peaks, one at for a very low Dalton, with respect to your sample, one at relatively high Dalton, and then one kind of in the middle, which should be hopefully a major peak in your system. So for this particular case, we can go through and select these peaks, and we have to identify what they are. So we have to use some known elements. Now in this steel sample, I know I have iron and I know I have carbon, so that should be really easy to pick out. So what I've done here is we've used for the kind of low end, we've looked at carbon in the 2+ charge state, which is at 6 Dalton. In the middle, for the major peak, we've chosen that iron 56 and 2+ at 28. And then for the high end, we've looked at iron 56 and the 1+, which is at 56. And you can see the difference between, before and after the mass calibration. There's a slight improvement in the location of our peaks. A good way to check this is to compare to a third element, one that is in your sample, but you didn't actually use as part of defining the mass calibration. So in this case, I know there's some nickel in the sample. I can look at one of the nickel 1+ peaks, and I can see it's shifted a little bit more after the mass calibration to be exactly where it should be. Even if you have small shifts like this, it's important to do it that way, if you are looking at, multiple data sets, especially with the same range file or so on, everything should be exactly where it should be. You don't have to treat everything on kind of a case-by-case basis. Then we go to the step of the ranged ion assignment, and I've kind of talked about this already, and how we go about, assigning the different peaks to the different elements. So I won't kind of go into this in more detail, other than just to kind of show it before and after. So the before, we only have the peaks identified that we used for our mass calibration, because of course those peaks, if we use them to calibrate, they should be, what we said they were. And then after, where we have everything else filled in, which includes, a series of, ions that are just elements, aluminum, iron, and so on, as well as molecular ions, combinations of carbon, C2, C3, C4, and so on, and other various combinations, until we have basically all the mass spectrum, the major peaks identified. Now we get into the spatial reconstruction aspect. So I'm just going to kind of walk through some of the different factors we have in here, what we'll do as inputs and so on. So first of all, we do have some material parameters that will go into our reconstruction. These are based, again, on the atomic volume of the specimen, and also some assumptions about the evaporation field, given the primary element and the temperature of this evaporation. We also will assume some instrument parameters. So here we have our input detection efficiency, which for this case shouldn't be too much of a variation from the nominal for this 4000 XHR leap, which is 0.36. We also can build our kind of specimen parameters. So these are inputs on kind of what the specimen shape was like. So here by default, we're looking at radius evolution using a voltage profile. It shows us what that kind of reconstruction voltage, initial voltage would be, and the resulting initial tip radius. And that's calculated, again, using that K factor, that field factor, and then also will be affected by the image compression factor. And those K factors and image compression factors, as it currently stands, are at their default values for IOS. So now, let's just say we built our reconstruction using all those default parameters, default field factor, default image compression factor, and using a radius profile, or voltage profile for our radius. We can take a look at our sample and see, okay, well, we've got, an iron-rich area on top, it's our ferrite, and we've got a carbon-rich area underneath, so that's our arsenic. And what we know is that these are very different materials. One's a metal, one's a non-metal, very different evaporation fields. And we can kind of see this when we look at the voltage profile as well. We kind of get a weird flat part and then kind of a curve going up. And if you look at that voltage curve and then the sample, you can see how the two of them are somewhat related. So, but we know though that this moving between these different phases would violate one of the assumptions of using the voltage profile, which is that we have a homogeneous evaporation field, or rather a relatively constant evaporation field, and such that we can expect constant proportionality between the voltage and the radius. And the result of this is, even though this recon still looks pretty good, some of the features are a little misshapen. We can see that interface is a bit curved. When we would expect that interface to be much more planar. So we can go in and try and improve this. And one of the things we can say is, okay, let's stop using the voltage curve then to define our radius. Let's instead, since especially we made these samples on the fib and we have images of them that we took right after sharpening, let's try using that tip profile. So we can map, calibrate an image, and it's tilt corrected and everything from this SEM image following fib sharpening, and build this radius profile from it. Now you can see that this isn't too detailed. We can't see the carbide within it directly from the SEM image. Also, I wouldn't always recommend trying to do extensive imaging on a tip after you finish sharpening it, and the risk of, depositing, some carbon on it with the E-beam. But overall, we have the overall shape that we can see here, and we can build that. So now what we can do is try and see if there's other factors we can do within this radius evolution profile to calibrate some of the other factors that will influence this reconstruction. And so for a tip profile reconstruction, we're looking at primarily the initial tip radius, so where we begin building this profile, and the image compression factor as the primary, primary other parameters that we would need to calibrate. Now, to look at this, we can go back to, as I mentioned before, and try and use a little bit of the information, crystallographic information from this sample to spatially calibrate our reconstruction. So if we look at the kind of early part of our data, which we know is the ferrite, we can isolate that portion. And if we see on the detector event histogram, we can see all these shapes that are representative of essentially the crystallography of the sample. So we can identify peaks known for basically BCC materials, in this case because BC iron, and identify those poles based on these established patterns. And so we can see an example of that on the bottom left, and this is using the pole indexing tool in IVAS, but you don't necessarily need to use that tool if you can readily identify what they are. So one of the poles we can use, for example, is that in that main cross, we have the 011 ferrite pole. Then what we can do is go to the Reconstruction Explorer and begin to adjust our reconstruction parameters until we get despacings that satisfy this material. So what we want to do in this case is look directly at the material at those poles, because that's where essentially we'll be able to build that spatial resolution the highest for those that plane spacing. So we define on the detector, we define a small region. Here we're taking only a 1 millimeter, and that's detector space, radius, and place that at detector XY coordinates where we see that pole. Then the other thing we do is we have to define a portion of the ion sequence that we're going to sample when we are looking at this reconstruction. So here, we've taken an ion sequence range of only 20%, so only a fifth of the data, and we're centering it at 25%, so we know that it will place it right within that ferrite region. And the reason, of course, that we're talking about this in terms of percentages is because at this stage of the reconstruction as inputs, we don't have Z coordinates. This is kind of pre-Z coordinates, reconstruction. So we can take this small amount of data, and then what we can also do is build the reconstruction projected about that point or from that point or centered for the projection. So then what this does is this builds in Z, essentially it sets up our Z to be equal to the direction of that pole, such that we can expect the planes to be normal to our Z axis. And then we can see that when we just even look at the reconstruction volume there that we're looking at, this small kind of subsample volume, can already begin to see, some essentially planes appearing, these kind of horizontal lines, and when we look at the distribution of the ions. But then what we can do when we want to measure the despacing, it's very hard to measure the despacing directly in Atom Probe, but what you can do is kind of measure it in aggregate. And so we can do this with a spatial distribution map. So what this is doing is essentially it's a histogram of measured distances along a given direction, in this case our Z, between every single ion in this subvolume that we're sampling. And so what this means is if we have two atoms that are on the same plane, the Z distance between them will essentially be 0, right? So that's why we have a very high spike, at the distance of 0 Z. And if two atoms are on adjacent planes or successive planes in Z, the distance between them should be roughly, just the Z distance between them will be roughly equal to 1D or 1D spacing. And then each of these other peaks occurs because if we're measuring to atoms that are 2 planes away or 3 planes away, we'll have distances of D, 2D, 3D, and so on. And it's symmetrical because, of course, the distance between an atom on the top and the bottom is the inverse of the atom, distance between an atom on the bottom and the top. So now we can take this measurement here of our despacing, and we can use it to help give us an image compression factor, that gives us a good representation of the crystal based on the known parameters for this material. And then we can use that to build a much better reconstruction. So this is the reconstruction that we would make from a tip profile recon of the sample using the poles that we've seen here to get us calibrated based on those plane spacings by adjusting the image compression factor and adjusting the R0 value initial radius. So you can see it's not too different than what we saw with the voltage profile, but it does show a better, better representation of material, especially even if we look at that interface, we can see it's very planar now. So it's quite a refined reconstruction. And it's this reconstruction that we can take and we can, really begin to run our analysis on. So in this case, let's say we were interested at the, segregation profile of the interface. We can take a little subvolume, begin to map the concentration over that interface, and begin to do all the other analysis we have on it. Because for this case, we're pretty confident that we have a good, idea of the both the spectral and spatial, calibration for this material. So with that, I'll leave the Atom Probe data analysis to a future webinar. So just to summarize a little bit about what we looked at today on reconstruction, just keeping in mind that basically acquiring the APT data is only the first half of the experiment. In order to be analyzed, the data has to first be reconstructed. Now, reconstruction requires processing both the spectral and spatial data to form that full 3D model of the original material with all of the elements identified. Now, most methods of spatial reconstruction will require assumptions to be made about the material and its evaporation behavior. And if a material violates those assumptions, either on a large scale or even at a small scale, as most materials of interest in engineering interest, scientific interest do, it will require that the reconstruction be adjusted or done in a way to account for this. So we can look at different reconstruction methods, be it even just changing the radius profile method, or bringing in other information to help calibrate. So either SEM or TEM images, other material knowledge that you have ahead of time, but also, of course, just keeping in mind that not every limitation can be overcome. In other words, a perfect reconstruction that is 100% accurate both globally and locally, it might not be achievable, or at least not kind of achievable on the first try. You might have to kind of go back and change things again and again, or in some cases you might even just have to apply some post-processing, to some small areas of the reconstruction once you've made it to better calibrate for your feature of interest. So overall, the Atom Probe data requires that the artifacts and limitations within it, originating from both the acquisition and the reconstruction, be understood in order to be analyzed properly. So always remember that when you're analyzing the Atom Probe data, as we can talk about later, we're just analyzing the 3D model that we built. And so essentially, if we do, if the evaporation goes well, if the reconstruction goes well, then we can take that a little bit further. But if we don't have, a very good evaporation, if we are not very confident in our reconstruction, then it's just important that as Atom Probe scientists, we know how far we can kind of trust this data and in terms of the conclusions that we can draw from it. So with that, I'd like to conclude the talk, and sorry for rushing in the beginning too much. I'm just really excited about Atom Probe, I guess. So I'd just like to kind of finish off by pointing you towards some references and sources. These are 3 texts that are all very good. I've been using a lot of the images from them earlier, so here's my credit to them right here, as well as some sources I presented today from Kamika. And I'd like to thank you very much for your attention, and I'll do my best to answer any questions you might have at this point.
Great, thanks, Brian. So currently I have no questions in the chat. So if you have a question, feel free to put it on the chat, or since we're a smaller group, if you want to just throw your mic on, you're more than welcome to ask that way as well.
Okay. I'll also add that if anybody has any other questions after, or if anybody is even watching the YouTube video of this later on and has questions for me, you can always contact me. My info is on the CCEM website, and I'd be happy to discuss.
Great. So there's one question on the slide assigning the main peak for, I think that's a typo, but bowl and voltage collection, maybe not. Should one avoid the peak originating from overlapping elements through the main peak?
So I believe the question is then asking if we're running the time of flight correction for a given peak, is there an issue if we have overlaps on that peak? And basically, no, not really, because essentially the system, as far as it's seeing, the issue on our end is that when we have overlaps, it's because we have different types of elements that will all they all will have essentially the identical time of flight. What we're doing when we're running those voltage and bowl corrections is we're just accounting for other variations that can affect that time of flight. But overall, it if we have an atom of, say, that integer multiple of mass and charge, it will be affected. Its time of flight will be affected similarly to to others that it would overlap with. So it's relatively safe. But overall, you should be using the kind of largest, most dominant element in your data to run that correction. So there shouldn't really be, or even if there is overlap, it should probably be minimal. So say if I'm running a steel and I'm using that iron peak, I would expect that even if I had significant overlap from something else, it's still going to be small compared to the amount of iron in there. But yeah, it should be safe. I hope that answered the question.
Great, thanks, Brian. So, all right. Oh, your sample worked well with 2 stacked phases. How would the correct procedure vary if the phases were next to each other?
So I guess the idea would be if the 2 phases were side by side. So like if I had, if I could just go back a couple slides then. So if instead of this sample where I have basically kind of, on top of each other versus if it was side by side with each other, how that would vary. Well, it would vary in a number of ways. First of all, it would probably vary when I fibbed it. You'd expect the sputter yield to be quite different between the two, which would lead to kind of probably not a very good tip shape from the very beginning. And like we said, getting a good tip shape is pretty much ideal because it affects so much in terms of the projected electric field and therefore our ability to properly spatially resolve everything. If it was, say, buried within and we had a good shape to begin with, it would depend a lot on essentially how well the 2 phases were evaporating relative to each other. If one was of a significantly different evaporation field than the other, then we could expect pretty severe aberrations in the data. If I were to skip all the way back, I don't know, maybe this is too long to go, we could expect essentially very severe local magnification. That image on the right is actually kind of showing what we have if we have one phase in between that's high field or low field that's sandwiched by 2 identical phases. But you can kind of extrapolate that to imagine if it's just one side-by-side phases that are high and low field. Yeah, we'd expect basically a pretty severe deviation from that ideal hemispherical geometry, and probably a very difficult data set to reconstruct, even if you could do it properly. So what I would suggest is essentially if you had a data set that contained that, you'd be very aware of the errors that are probably in there that you would have to correct for. And so maybe, look to other areas in the data or look to a different data set as well if you need really good information, a spatial or even composition in that case at that interface. And if it's something that you're doing intentionally, like say when you're making your sample using the fib, I would highly suggest you avoid such an orientation, because you can foresee these problems ahead of time, in varying in different evaporation fields and having them side by side and try to put them as we did, where we have one face, and the other face stacked on top of each other.